Imagine that we take a soil mass inside the balloon and we squeeze it. That would be isotropic confinement. We could also place it inside a very thick ring and to enforce zero lateral strain deformation, and that is epsilon horizontal equal to zero loading. And now we're going to take the other case, which is the situation where we take a cylindrical specimen and we apply isotropic confinement. Without it, the soil cannot take any deviatoric load. And then we apply a deviatoric loading to force the specimen to become shorter and fatter, eventually to reach the maximum load. This is the case that we'll be talking today. Clearly, this case is going to reach failure. So let me refresh a couple of concepts. The first one is that if I show the system in the applied shear stress with respect to the mean confinement, where the mean confinement is confinement that I apply to the specimen, then when it reaches failure, this is going to be along a line which is tau ultimate equal to sigma tangent phi, where this is the friction angle or the angle of internal shear strength. Second, we are going to talk about the state of stress at the point in equilibrium, where this is sigma 1, this is sigma 3, which happens to be the sigma confinement in that experiment, and this is the amount that I deviate from isotropic stress, so this is sigma deviatoric. Therefore, tau maximum is equal to sigma deviatoric divided by 2. We are going to follow the specimen and its behavior from the moment that I apply the isotropic stress and throughout the application of the deviatoric load. So if we do that for a large number of circles, then this will become a black spot. Consequently, I'm just going to follow the apex, and we're going to call that the stress path. Now, the coordinates of the apex, as you may remember, are the height is equal to sigma 1 minus sigma 3 divided by 2. This is Q, sigma 1 minus sigma 3 divided by 2. While the position of the apex is the distance from the origin to the horizontal position of the apex, is it going to be equal to sigma 1 plus sigma 3 over 2. And these are the QP coordinates coming from Mohr circle. If you read the literature, you will see that there is another Q and P definition coming from the UK, and is extensively used in many parts of the world. And therefore, you have to be careful because, once again, these are the PQ definitions primarily used originating from the US and coming from Mohr circle. The stories are quite similar. The difference is that the QP coming from the UK is based on the octahedral state of stress, so takes into consideration not only sigma 1 and sigma 3, but also the intermediate stress, sigma 2. And so it's defined in the octahedral state of stress. Nevertheless, what I'm going to say today pretty much applies regardless of the definition of P and Q. The second observation is that when the triaxial device was developed in the 1932 through 1936 by Casagrande and used first by Terzaghi. But one of the things that Casagrande was able to observe was that during loading, the specimen was changing volume. That was not clearly observed in the absence of a triaxial test. To some extent in shear, but not so effectively. And therefore, he recognized that materials change volume, but it depended on how dense they were at the beginning. So if he took a loose specimen, it would behave like that under sigma deviatoric epsilon z, but a dense specimen would behave like that. Eventually, at large deformation, both of them would reach a similar asymptotic strength, while the dense specimen had reached a higher value, which is the peak strength. Now, when you plot what happens with void ratio in the same axis, this is void ratio. Let's say that this is the loose and this is the dense specimen. The loose specimen starts with a higher void ratio, so this is E for the loose specimen, this is E for the dense specimen. When he monitored the changes in void ratio, that means that the volumetric changes, the loose specimen contracted to an asymptotic value. The dense specimen may have contracted a little bit at the beginning, but then it dilated to the same asymptotic value. And that became the concept of a critical void ratio, where the two specimens converge when subjected to the same isotropic confinement. So now we're going to put all these concepts together, and we will try to follow the behavior of a soil in a QP space of, or tau sigma space, as well as in the deformation deviatoric strain and volumetric strains, which is represented by void ratio. Once again, if you ever get lost when we are dealing with Q and P, and I just show you a point, always realize that you can lower that point, find the center of a circle and draw the circle around that point represents. Therefore, we can always talk that this axis is both sigma if you are drawing more circles, or P if you are drawing the apex, and tau if you are drawing more circle, or Q if you are drawing the apex. Before I leave this section, I would like to make one more observation. There will be changes in the pore pressure when you do the test undrained. And so we are really interested in what is the soil skeleton experiencing, because the water cannot take any shear. It's really the soil skeleton that takes the shear. So we always have to be wondering, what is the soil skeleton effectively feeling? And so instead of just working with Q and P, we would like to work with Q prime and P prime, where this is going to be sigma 1 effective and minus sigma 3 effective over 2. And this is going to be to sigma 1 effective plus sigma 3 effective over 2. Now let's expand this. This is sigma 1 minus u and minus sigma 3 minus u. So when I remove the parentheses, this becomes sigma 1 minus sigma 3 over 2 equal to Q. So Q prime is equal to Q, and it has to be because the water is taking no shear. So in terms of the shear component, the effect of the water vanishes, but when we do the same here, is sigma 1 minus u minus plus sigma 3 minus u over 2. Now I get that this is sigma 1 plus sigma 3, the total applied, externally applied stress over 2, and then I have minus 2u's over 2, which is minus u. Therefore, P prime is equal to P minus u. This will become clearer as we advance into the drain and undrained behavior when we compare both of them. So in the next window, we're going to show the drain behavior. What is drained or undrained? Once again, let's be clear. Drained is when you load slower than the water can escape in or escape out or come in. Drain out or drain in. So drain is when the rate of loading is much slower than the rate of pore pressure changes. That means that the water can freely drain, while undrained is when the rate of loading is faster than the rate of pore pressure dissipation. This being rates, that means du dt. The story gets more complex when we bring this to the reality of a field, because the drainage path may be very long, but also there may be pockets that may be dilating or contracting, and drainage is taking place internally rather than involving the boundaries. So it may be globally undrained, but locally drained. In the 40s, Casagrande at Harvard and Taylor at MIT decided to embark on a project trying to identify the parameters that determine that critical void ratio and what controls it. Intuitively, we say, well, if the soil tends to dilate or if it tends to contract, it's because it is either very dense or very loose. But imagine yourselves being in an elevator and somebody behind you is trying to come out. If there are only 2 or 3 people, you move to the side and the person can come out. However, if a person wants to come out and is all the way in the back in a packed elevator, few people will have to exit for the individual to come out. That is dilation. However, if for whatever reason there is very high pressure and you cannot expand, and that person still has to come out, well, you're going to squeeze yourselves for that person to exit. So under high pressure, there will be no dilation. And so all of a sudden now, we realize that if we plot Q versus P prime, this is the failure line, which, as you remember, and go back to the more circles, but this is now the alpha line, so sine phi is equal to tangent alpha. And that is where all soils will fail when the tau sigma QP conditions touch the failure envelope. So this is the failure envelope, the Coulomb failure envelope now defined in the QP space. Now, summarizing the previous discussion related to the elevator, we realized that if soils have a large void ratio, they will tend to contract. But they will also tend to contract if they have a high confining pressure. Therefore, we can pretty much split this space in 2 regions. High void ratio, high confinement, this is contractive. Low void ratio, low confinement, this will be the dilative regime. Interestingly, all soils will fail volumetrically, will tend to go to this line in the EP space, volume confinement space. From the point of view of shear strength, they will go to that line. So eventually, at failure, a point that represents the soil will be touching that line and will be touching this void ratio confinement line. What this is telling us is that what we see here is a projection of one single line that is cutting across the octate of a space. So if we put here void ratio, and this is P prime, this is Q, now we realize that in the horizontal plane, which is EP prime, this is where all soils end. On the vertical projection, the QP prime, this is where all soils end. And now what we are saying is, these two are the projections of the true line in the PQE space where all soils end. And indeed, this is the case. This line traverses the space, and it would be as follows. I hope you can visualize the 3-dimensionality. I'm referring to this line here, and it is the true end position and location for the soil at failure. So coming from Coulomb, we realized where the soils were failing in shear confinement space. Coming from Casagrande, Taylor, and Taylor 1948 book, we see where that happens in the volume confining stress space, and these two are just the projections of the true end line in the volume shear confining space. And that led to critical state soil mechanics, Schofield and Roth, and the multiple further derivations in geomechanics. So now we are ready to address a situation where soils are going to be subjected to drain deviatoric loading. So we are going to take as an example the drained case when we subject a specimen to axial compression. For clarity, we start first with a tau sigma space, and we are going to apply isotropic confinement. Once we reach isotropic confinement, the specimen is under sigma 0 in all directions. We are going to begin adding sigma deviatoric. So this quantity here is sigma deviatoric. Therefore, the apex Q is equal to sigma deviatoric divided by 2, and that is the specimen under sigma deviatoric. Now, if you follow all the multiple circles, you realize that we are moving on a 1-to-1 axis, in other words, at 45-degree angles in the QP space. Furthermore, when you run the test, you apply the sigma deviatoric and you measure the deformation. Deformation divided by the initial length gives you the strain. And so now we're going to have an interesting case where on the one hand we have Q and P prime. On the other hand, we have the void ratio, but we are also going to plot epsilon deviatoric, or epsilon in the z direction, the shortening of that specimen with the application of the deviatoric load. Let's put some of the boundaries. This is the alpha line, which is Q is equal to P prime tangent phi, which is totally identical to tau ultimate equal to sigma tangent phi. And here is the projection, the horizontal projection of the failure line, which runs in this plane. So let's start with the following situation. We take a specimen and we are going to load it to this isotropic stress. Sigma vertical equal to sigma horizontal, so P is equal to sigma confinement up to this point. And we're going to say that the specimen is contractive. If it is contractive, it's either because the void ratio is too high or the p-value is too high, and therefore the projection of that point on this plane is going to be here. This is the contractive specimen. We control the load, and so, because it's drained, everything that we do is felt by the soil skeleton. So we apply the load, and we know exactly where this is going to fail. It's going to fail at this point following a 1-to-1 line. Now, if we fail at that line is the vertical projection, and this is the horizontal projection of the same line. That means that there has to be the point on the other projection where the soil went to fail. Now, how did it go in this space? I don't know. That's the beauty of the triaxial test. We actually measure how much water comes out of the specimen in this contractive specimen, and I can determine the volumetric changes. But at the beginning, this is going to contract quite rapidly and then asymptotically go to the failure line. So I'm guessing that it's going in that direction. So let's be clear. We are going to measure the volume change, but we are going to impose sigma deviatoric. So I know exactly this plane. This one is the one I need to measure. Now, what are the other projections? Well, the other projection, this line is going to come. This soil goes to, the more it contracts, the more interparticle contact. The more interparticle contact, the higher the friction that has to be mobilized, the stronger it is, but it goes towards an asymptotic condition, which is that behavior. And in this other space, starts at this void ratio, and it will end at this void ratio. So it just contracts, and it goes like that. This is the response of a contractive soil. It could be a clay or a sand, a soft clay or a loose sand. The behavior of a contractive soil during deviatoric loading under drained conditions. If you remember the previous screen, I was showing the fact that dilative soils actually go to a peak before they soften to reach the shear at constant volume. So how does this manifest in this case? We confine the specimen, but we have to recognize that that specimen is going to be under dilative conditions. So it's going to be somewhere here. This is the initial point, and that is the initial point. The soil will, in order to highlight the colors, I'm going to wiggle the lines, but unfortunately colors do not capture the whole detail, so please follow it carefully. So it will go up, overshoots, and then it comes down. That is the dilative soil, and the dilative soil will end up at the same point as the contractive soil. So that point projects at the same position, but it will go from this initial void ratio to that final void ratio, so it will be dilation. But at the beginning, it gets rearranged a little bit, so it may actually contract a little bit. It contracts, and then it's going to expand. But notice that it overshoots. So it's actually going to contract and go like that, and then return to reach the failure plane, the failure point. How does it manifest in the other diagrams? Well, it's going to reach a peak strength somewhere here, so it's going to be like that. Please recognize that I'm making this crooked line so we can identify the different trends. And what happens in the volumetric versus deviatoric strain? At the beginning, it's going to contract a little bit before it expands, and at the peak is where the maximum rate of expansion takes place. So this is the maximum rate of expansion. This actually gives me the angle of dilation. So from alpha, I know the friction angle at constant volume shear, and from phi, I determine the angle of dilation. So I could plot a line here that goes through the peaks, and the slope of that line, if we convert it to tau sigma, the slope of that line, this alpha, we're going to call it alpha peak, alpha peak will give me a phi peak, and that phi peak is going to be the friction angle at constant volume shear, friction angle at constant volume shear, plus fraction of, so let's say a value A of the angle of dilation. And you can go to Bolton's classical paper, 1986, to see evidence of that. To summarize, this is the drain behavior of a dense and a loose soil subjected to deviatoric axial compression loading. At the beginning, we confine it isotropically. Then we apply the deviatoric loading, which in the PQ space becomes a 45-degree angle line. The contractive material goes asymptotically to its limit, gradually evolves to the asymptotic values, both in strength and in volume change. The dilative material it actually has to climb. Particles have to climb in front of their, over the particles in front of them. So there is a volume dilation that takes place. You have to add energy demand, not only for friction, but also for volume expansion. You are working against the confinement. And so it gives you higher strength before it returns to constant volume shear. There is a little bit of contraction at the beginning and then dilation, and that completes the plot. Once again, I highlight that at the maximum rate of dilation is where dilation is contributing to constant volume shear, so you have a higher strength that gives rise to this equation. The next case is when we load the system undrained. So let's be clear. We are going to apply the isotropic confinement under drained conditions, but then the deviatoric load will happen under undrained conditions. Imagine that there is already, the soil is already there on the ground in equilibrium. That means it's feeling all the effective stress, and at that point you come and place a building faster than the rate of pore pressure dissipation. It's not identically the case because you are not starting from an isotropic state of stress, and we can take that into consideration, but that is pretty much a situation we are trying to represent. Once again, we are going to go into the fourth dimensional space where we have Q and void ratio, and that means tracking the volume. Here we have P prime and the deviatoric strain, the vertical strain. This is the failure envelope at an angle alpha related to phi through sine phi equal tangent alpha. And this is these are the two projections, in fact, of the ultimate line where soils fail in the three-dimensional QPE space. So let's apply the isotropic confinement. So a given soil is going to be under isotropic confinement at this point. And now we are going to apply the deviatoric stress under undrained conditions. But let's start by deciding which case do we want to analyze first. So let's say that we start with, this is the dilative regime, this is the contractive part of the space. We're going to start with a specimen that is decisively contractive. Under undrained conditions, the soil wants to contract, but the water cannot escape. So there is pore pressure buildup. And so the effective stress changes. You think that you're applying sigma 0, but that sigma 0 is not going to the soil because part of it is taken by the water. So you are controlling the external stresses, but you are not controlling the internal evolution of the process. So we don't know where the soil is going in this space because we do not know what is the effective P unless you measure the pore pressure. On the other hand, you do know where the soil is going to fail here because under undrained conditions means that the epsilon volumetric is equal to 0. There are no volume changes. It means that the void ratio will remain constant during shear. By the way, there are important unstated assumptions there. Like, for example, that particles are perfectly rigid and that the water is perfectly rigid. Under those assumptions, then what we know is that this soil will go to failure while we're loading it, but the only way that that soil can go to failure at constant void ratio is to move in this direction. So this is where the soil will find failure. You think you were loading the soil in this direction. Internally, the soil is not feeling that stress because this point here now must have a projection on this point there. And so what happened is you were loading the soil in this direction at 45-degree angle. So what happens is that probably started going in that direction, and as soon as it did that, the soil began contracting, began building up pore pressure, and the sediment kind of collapsed. And in fact, the strength at the end could be very low, and it could behave like a liquid, and that is, in fact, another word that Casagrande introduced, liquefaction. Not in the same semantics as is currently being used. So this is the behavior or the response of a contractive soil subjected to deviatoric loading. At any point, you may remember that P prime is equal to P minus U. So what you're applying is along these lines. So at any point, I can compare what is P prime compared to this value. And then on this graph, I'm using P prime for the true stress path, P for what I'm imposing. So the distance between these two, which is P prime and P, is U. So this is the excess pore pressure being generated, is that distance there. Now, how does the plot look on this axis? Well, starts at this void ratio, ends at that void ratio, so this is a flat line. How does it look on the deviatoric stress versus strain? It will start at this point, it will end at that, and it reaches a point, a peak at this value. So I don't know, I have to measure it, but it will look something like that. What you see here is the soil response to deviatoric loading under undrained conditions for a contractive specimen. Let's consider next the dilative specimen. We're going to subject it to the same isotropic effective confinement, but the specimen is going to have this initial void ratio. Remember that the dilative specimen, in almost all cases, as soon as you begin shearing it, it tends to densify a little bit. If it wants to densify, it will have to squeeze water out, but the water cannot go out because it is undrained, and therefore it will build up positive pore pressure. And so at the beginning, I jumped too fast. Let's start with what we know. What do we know? That the soil will shear at zero volumetric strain at constant void ratio. Therefore, I don't know what will happen at the top, but I know here where the soil will find the failure line, which is at constant void ratio. It will go up to this point. So now, let's see how is that going to look. So this is going to be a point on the failure line here. We know the extreme, but how does it go from this point to that point? I don't know, I have to measure. I have to measure the pore pressure generation in the triaxial cell. By the way, how do we do that? We have the triaxial specimen inside the triaxial cell, and as I apply the deviatoric load, the valve is closed, but I have a pore pressure transducer, and I measure the pore pressure generation in a rigid system. And I'm going to see that at the beginning, it goes a little bit towards the left of the line because it's building up positive pore pressure. But then very soon thereafter, it's going to start trying to dilate. It can't. It wants to dilate, but it can't because I'm enforcing constant void ratio. And so it's going to generate negative pore pressure until it goes to the failure line. And now at any point, I can use the expression P prime equal P minus U to recognize that that is negative pore pressure. So where did the soil fail from a deviatoric stress versus a strain? It will be like that. And how does it look in terms of volume deviatoric strain? Well, it's horizontal line. Summary. The undrained behavior is totally matched and a consequence of the drained behavior. but it captures the coupling between the pore fluid and the granular skeleton. If it is undrained shear, it will shear at constant volume in that extreme case of perfectly rigid mineral and perfectly rigid liquid, water. And so we do know where the soil will encounter the failure line. So this is what we know. And we will have to measure the pore pressure to see how P prime is evolving. In any case, the contractive one will build a positive pore pressure, and the higher the pore pressure, the higher the effective stress, the lower the effective stress. The lower the effective stress, the lower the strength. So we can go back to our standard equations. Effective stress is equal to sigma minus u, and tau ultimate is equal to sigma effective tangent phi. So as the pore pressure increases, the effective stress decreases, P prime decreases, and because the effective stress decreases, the strength decreases. In the case of the dilative soil, in total agreement with the drain case, at the beginning it tries to contract, but it really can't, so it will be the positive pore pressure. It will be to the left of the total stress line of what we are externally imposing. But then, very soon, we'll recognize that in order to continue deforming, it has to dilate, but it can't. It wants to dilate, but it cannot pull water in, so the water goes into tension. And that tension adds to the effective stress because the pore pressure decreases, the effective stress increases, the effective stress increases, the strength increases. There are few interesting cases of this. For example, the contractive behavior and the very low residual strength during undrained shear would correspond to a loose sand or a soft clay. On the other hand, the dilative response will be reflected by a highly overconsolidated clay, probably more than 3 or 4 overconsolidation ratio, so a stiff clay, or a dense sand. The other observation that we want to make is that sometimes the pore pressure that we generate is, the negative pore pressure is so low that the pore pressure drops below 100 kPa. That means that the water goes in such a tension that it breaks down, bubbles form. And if that's the case, now the pore pressure vanishes, and you may see a drop in strength, and that drop in strength is because of cavitation. That happens when the sediments are truly dilative. In the laboratory, we can prevent cavitation by running the test with back pressure saturation.